Hi, thank you, Stelio. Thank you everyone for coming here and online. So the topic of today is a continuation somehow what we learned yesterday on the usage of GPU, but this time we will use Python instead of C and compiled languages. Most of these workshop that we will have now in two sessions, one for an hour and a half now and then an hour later, is going to be mostly focused on hands-on exercises, very few slides here. All the rest we will see it live doing examples using Jupyter notebooks. I divided the topics into parts. One, we will see how to do GPU programming using Cupy, that is a package supported directly by NVIDIA. And then we will see the usage of Numba for compiling kernels. So before moving now to the practice, let's just an introduction to the first element, that is Cupy. The purpose of it is to provide a complete Numpy and SciPy API coverage, which means I suppose most of you are familiar with Python and most of you have used during your developments either Numpy or SciPy. And these are the most used package in the Python world. And what Cupy aims to is to provide an API that covers all the features of these two packages and follows exactly the same API in order to be then a drop-in replacement for those. So namely, what you should do in your scripts is, for instance, use import Cupy SCP, and then the CP will act as one-to-one as a Numpy module, as you will do for import Numpy as NP. In the same way, you can say from CupyX import SciPy, and within SciPy you will find all the functions provided by the SciPy package, but now these will run on GPUs. So this is the theory. Now let's see how this goes in practice. And I will move to the notebook. So please, if there are any questions, interrupt me and just ask, both here online. So, okay. In general, I would say you're all familiar with Python. We don't need to go deeper into that. So ideally, what you will do, for instance, with NumPy, when you want to sum two arrays, is to create these arrays and then sum them. This is better to be done in NumPy with respect to doing loops in Python, because what you will do when you call the sum operation is a compiled kernel that will execute with sum all the array directly in one call, instead of having to write a for loop that goes over the elements. So what you will do usually is say for I in range of len of xi, you want to do, for instance, you want to do out equal out of y equal xi. That's the. So this is something you should never do in Python, basic, namely writing explicit for loops, right? So now out, I didn't declare it, but we can, well, okay, it's not the purpose of this training to go through that. Just the point is that you should never write for loops when you do, and the best way to perform scientific operation is then to use NumPy, and these will run on CPU. In the same way, you can do the same operation with Cupy. As we said, this is meant to be a drop-in replacement. So you just have, instead of using NumPy, use Cupy. And now when you call cp.
Simone,
Yeah.
Good morning. Can I ask if you have to iterate through an Numpy array and you have to make some operations, for example, with the previous or the next and the current subscript. So the way you do it is to store 3 different arrays and then make the operation, or this is or there is a more optimal way.
Can you repeat that just to understand better what?
If for example in your C code you write xi plus xi plus 1.
Okay.
And you have to you do the for loop in your C code, but in Python, what you do, you write the arrays, you write 2 different arrays and then you add them, for example.
Okay. Yeah. Okay. This is a good question. It's we can see it after. So basically, what you're asking is how to do such an operation efficiently in Python.
Yeah.
To do it in Numpy is, for instance, so you get, let's take this array that is x1. Basically, you want to sum it with the next element. What Numpy offers you is the roll.
Yes.
So you will roll it of 1. In this case, if you want the forward, it's -1. And basically, you see that the first element went last, and this is the
okay.
1, and then you do x1 plus this array. And this is the sum of, these are kind of this kernel where you apply a stencil between I and I plus 1.
Okay, okay. So you don't have to copy and paste in, I mean...
anything you want to do, you can find the Numpy function that does it for you. This is not the most efficient way, though.
It's not okay.
Let's say this goes in another direction, but okay, let's spend a minute on this since you asked. This is not the most efficient way, because what Python is going to do under the hoods is to create a new array. So this step creates an array that then it's added element-wise to the other. It's much more efficient than the loop, for sure, but it's not as efficient as in C, where you wouldn't create a new array, but you would access the element and the next.
Yes.
We can see afterwards. Ask me again afterwards when we move to Numba.
Okay. I don't want to delay you. Okay, thanks.
We can see also, but during the hands-on, this could be something. If you have any question about specific kernels, we can discuss them.
Okay.
So anyway, going back to the example here. So just okay, I can still give you an example as well with roll. Basically, what Cupy offers you, it's a drop-in implementation. When you say now CP and you say cp.random.rand, now this initialization of the arrays is not going to be done anymore on CPU, but on GPU. So like you saw yesterday, these are going to be allocated, device pointer, and they will be allocated on GPU, and any operation you will do between them, it's actually a kernel. Okay. So basically, when I run this, now that I'm on a login node, so this is running now on the node. And when I run this, it took some time just because it had to load the package. But if I run it again, it's immediate. So when I run this, now it's going to run on GPU. Of course, you need to have a GPU available. And we will see how to install it in a second. Or maybe let's just, let's just see it now. So basically, the Cupy is a package that if I'm not on a login node, so let's suppose I go on Cyclone and I go here where I prepared the view and I load my modules. Now I will go over these again, just to give you an idea. So if I start Python and not on a login node, let's say import Cupy, it will give me an error that basically it cannot find the libcuda.so because I'm not on a on a computing node where there is a GPU available and this is not going to run. So clearly, if you want to do anything with Cupy, you must have a GPU available and a CUDA installation. That's the point. But once you have it and you are interactive in a node, you submit job to a computing node, then anything that involves Cupy can be run, like here, and you are running basically on GPU. So this is what they want to offer you with the package Cupy. It's really a drop-in replacement. So the same thing that we did here now. If I do it again with Cupy, now X1 is an array located on device. The only thing I need to be careful to do is to replace NP with CP. And these operations now are performed on GPU. Okay. And ideally, what you want to do in your code, for instance, is to have a snapshot like this at the beginning, which says if we want to use GPU or the device or not. And if we use the device, we import Cupy as XP. Otherwise, we import Numpy as XP. So usually people use XP. And everything we did right now can be then generalized by basically just saying xp.random, and now either this is going to run on device because we say use GPU equal true, but if I say equal false, then this guy is going to be run on CPU. How can you know that it has run on device or not? Well, like this, you cannot know it really. So the only thing you can do maybe is to ask the type of X1. And if you ask the type of X1, in this case, it's a Numpy in the array. When if now I'm on device, the type of X1, it's a Cupy in the array. Okay. But this is somehow the power of Python that wants to be completely agnostic and user-friendly and provide an interface that is easy to use. Clearly, if everything was so easy, there is no reason to have a 3-hour training, 3-hour introduction to this topic, because the answer would be just use Cupy instead of Numpy, and you're going to run on device. Okay. Therefore, now we are going to dig deeper into this concept. Before proceeding, are there any question about this?
Sorry, one question. Yeah. The option use GPU has meaning, of course, if we have GPU on the.
Of course, maybe what you want to replace instead of true is to have a function that says check if we have the GPU, if we have GPU available, let's say, and then if you have such a function, you are using GPU, otherwise not. Suppose this could be an option. Okay. Yeah. Okay. I mean, the other way, like we saw, the best would be to say try this. Then we saw that if you are not on a login node, you get an error, so you have an import error. And what you will do then is to say try this, except import error, and you are going to use XP. So this will be a generic line to put at the beginning of your code, and you try to load Cupy. If cannot, you use Numpy. But the point is that we are going to see that it's not always optimal to use Cupy and run on GPU, even if they're available. Okay. So what you want to aim to mostly is an hybrid code that uses both. Okay. So this is the point. Other questions? Okay, then I proceed. So let's have a first look at performance. By the way, is it fine for everybody the size of the font? I guess also online you can see it well. You can increase otherwise. Let's have a look at first look at performance. Here I'm using somehow I made it a bit more complicated than what it could be, but it is a procedure for now measuring the performance on increasing size. We'll go just rapidly to the lines. Basically, we are going to use the package timeit for timing the code. We use pandas data frame to just store our results. And we use data frame because they provide some nice function for plotting and visualizing the tables, results, etc. And basically, we create a data frame which has a size that goes with powers of 2. So I'm doing 2 to the power I from 0 to 23. So basically, we are going through elements to arrays that have size 1 up to the 2 to the 23. Okay, which is this number. It's about 8 million elements. And we go through these sizes, and then we call the same function. We time basically the same function using both Numpy and Cupy. Okay. For doing so, the only difference is the creation of the array. So one is created first with Numpy, then with Cupy, and we sum them together. So if I execute this, it's going to take a few seconds, and it's going to give us then a plot which have the performance of the two. It took some time because clearly as more as we go larger, this is going to take much more. So the last point may take more than all the others put together. We are doing 100 iterations just to average and the average between them, just to have some to reduce some noise. And basically what we are seeing is that while the Numpy kernel has at the beginning some overheads. So up to here, okay, how to read such a plot? Up to here, when the line is flat, so the time is constant, we name this overhead because we are not measuring the actual time per operation. And this is just what you are seeing is basically the time for calling such operation. And then all the rest is the time actually for doing the calculation is minimal, and it's covered by this. So the constant value is the overhead. And then when we have a linear increase like here, this is then the cost, how many of these operations we can do per second. Then this is a representative of how many operations we can do per second. Okay, Numpy, it's increasing drastically after a size 1000 of the array. This is for the sum, while Cupy is constant. So basically, we are just seeing overheads for Cupy. Okay. Let's get some more information. So like I said, these times basically, it's a table now that we have constructed. Data frame where we have for Numpy and Cupy the various sizes and their timings. So you can really see that for Cupy it's constant. There is no change in value. Now we can do some more elaboration of these timings. So for instance, if we want to get, let's say, a speed up, suppose, of we want to get the speed up of Cupy versus Numpy, for instance, I can, what we are going to do is to, okay, we apply a transformation to these timings, and we basically divide the time of Numpy with the time that we get from Cupy. This is going to then give us a plot like this one, where now it's this is speed up versus Numpy. And we can see that now, for instance, Cupy, it's order of thousands times faster than Numpy. So we just did the ratio between one and the other. Other analysis that we can do is, for instance, getting the performance of it. So we divide the number of operations we are doing by the time we get, or we can get the bandwidth and we want to divide similar like the performance, but the data size of the array by the time that we by the time that it takes. So these are various metrics. As an endful function that I'm going to use afterward, I define this show times that is going to elaborate these. And okay, it's defined this cell. You can find, by the way, you can find everything online under the GitHub page on day 2. I will not go into detail of this function. This is just for showing some of these results. But basically now calling show times, this is going to be the result. So we have the plot of the times that we saw before, below the table that give us the results, that give us the numbers. The speed up versus Numpy, again, we have the speed up of Cupy that we saw that can reach up to 2,700 times faster than Numpy, and in this plot. Or, for instance, the performance that is measured in gigaflops, and we are seeing that Cupy will reach 965 gigaflops, so almost 1 teraflop. And the bandwidth that if we take Cupy, then we see that this could reach 23 terabytes per second. Well, though yesterday you learned that the expected performance of the devices is about 900 gigabytes per second. So the expected bandwidth. So maybe there is something wrong, or was yesterday Yannis wrong about telling you what is the bandwidth that you can measure on, you can get on the P100 we have on Cyclone. So does anybody have an idea what I'm either doing wrong or yeah, in this analysis? It's something that also Yannis showed you yesterday. So if you any suggestion?
We're timing it asynchronously.
Exactly. Who was Nicolas?
Yeah.
Yeah, exactly. So exactly, like you learned yesterday, the device, the GPU kernels, anyway, CUDA kernels in this audio structure, they run asynchronously. So basically you can offload as many tasks as you want to the device. Then you have a task manager on the device that will manage the execution of this task. But on the other hand, your CPU does not have to wait for this for the results to come. So it can proceed. You can proceed and keep going. And okay, so we have a problem because now the time is actually timing the CPU time, so the time for launching the kernel, and not the time for actually performing the kernel. This is why it's completely fast and will be fast forever, up to when the device then cannot execute anymore because it's out of memory. So how to fix this? Now, we saw it before. If we say when we execute this cell, we are getting actually a result. Okay. So what is the point here? Why I told you that it's done asynchronous. So when I call this operation, the results are computed asynchronous by the device, but somehow what I'm showing here is that we are getting the results. So again, I'm contradicting somehow myself. What is happening here? Basically, as far as you call the add, so how does Jupyter works? What is it showing here? Okay, that is going to be stored in a variable which is named underscore, but this is just for the purpose of the notebook. So the value of underscore is the value of the last cell. Anyway, this is what Jupyter is going to do. So it's going to do this operation. Let's say it's going to do y equal this. And then is going to show y by calling the representation of the string of y, which is going to, if I call representation, I'm going to get this. Basically, what the Cupy API is doing this operation asynchronously. But of course, once you have its value, it has to wait to get the array to finish the operation, and then can print the value. Okay, the same result basically you can achieve it by using y.get. And if I store y, if I call y.get and I say y.get yCPU equal y.get, basically what we are getting now, I name it yCPU exactly because this is now a CPU array. So if the type of this is Numpy, okay? So the get operation, it's going to wait for the result to finish and copy it back to the CPU. Okay, let's give it a try then. So instead of printing, let's say I get it. Okay. Now, what do you expect? Expect somehow the time to increase because we are actually doing the operation. But okay, now the timing is increasing as much as Numpy. Actually, you're seeing the overhead and then a cost that is the same of Numpy. So again, just getting the rates not really represented what we are doing on device, because what are we adding now to this operation? It's not just the cost of the kernel, but we are also adding the device to host copy. So this is why it's more expensive. So the cost you're seeing is actually the cost for not for doing the calculation, but for copying the device to host, for copying the array from device to host. So this is another thing that you don't want to do, clearly. Okay. So basically, you never want to go out of the device. When you are dealing with Cupy, of course, if you're going to do some debugging, you want to test your code, it's always good to print stuff and check what is happening. But on the other hand, as far as you work with Cupy's array, you never want to go out of the device. You want always to stay in device. Never call get, never call never call other functions like print, etc., because these are going to synchronize the device and then get everything, etc. So this is going to slow down your code. Okay, so how shall we then benchmark our device code? Not with get, not with just calling the function. The way is to do something similar to what you saw in yesterday with Jan, is to use to call the CUDA synchronizer for just synchronize, for just making sure the calculation is finished. But we are not going to use this low-level function. We are going to now use what is provided by Cupy itself, that is this benchmark function. Okay, so the benchmark function will benchmark the kernel in a similar way like time it is doing. We say how many times to repeat it, and then we return as two arrays. One is the CPU time, so the time spent on CPU, and one is the GPU time, so the time spent on GPU. Okay, I'm going to show you. Let's run it a second to see the results. So basically, at the moment, I'm just summing, then dividing, so meaning the GPU timing. And let's see now what is the performance of the actual performance on GPU memory. Yeah, on the GPU devices. Okay, this is representative of the time is taken to Cupy to actually doing the calculation. And you can see again, we have overheads and then a linear increase. Everything nice. So the calculation, the cost of the calculation start to be meaningful due to this very large overhead at about around more than 10,000, around 20,000 items in case of double precision. Let's see if everything makes sense now. So we have a speed up compared to Numpy of order 95, or a factor of 100. We have a performance in gigaflops that is about 33.5 gigaflops. And we have a bandwidth that it's very close to saturate the expected bandwidth, which is around 800 gigaflops per second, gigabytes per second. So we can see that this operation x plus y is memory bounded, and the bounded is the one saturating first, which then saturates also the performance. So the expected performance actually is much higher, the peak performance that these devices can give us. Okay, any question?
So this basically tells us that to use GPU within Python is meaningful if you have very large arrays, right?
Okay, but this is something that is true for everything. Also in also in C in compiled code, there are overheads on executing a kernel, and when you run on GPU, you want to fill up the GPU. Otherwise, you're not fulfilling the purpose of the device. So yeah, I have some slides about that, the difference between CPU and GPU, but basically the CPU is meant for very fast but very complex operation of single elements, while the device, the GPU, is meant for simple operation on as many in a very large amount of elements. So yeah, there is always this difference in both cases.
I guess there might be a better way to exploit it by manipulating the number of threads, like in like
okay,
in C.
Yeah, this is a very good question. Yes, there will be, but everything that Cupy does at this level cannot be manipulated, cannot be I mean, in all these kernels, the user cannot choose the number of blocks and threads. This is chosen by default, neither by Numpy itself, but by CUDA. So basically, the CUDA provides you many libraries that you can use. For instance, there is CUBLAS, that is an implementation of the basic linear algebra routines on GPUs. And also here, the idea is to provide the most user-friendly as possible library, which is already optimized for the size of the array you want to use. So all the kernels are already optimized. You don't have to provide the number of threads of blocks.
So it does them automatically.
Yeah, there is neither a tuning procedure. Just NVIDIA knows that given that specific model of GPU, and given the size of the array, the optimal number of block and threads is such. So it's an information that they don't give you, but it's in there, and they.
So it's not. We cannot manipulate the end threads as we did in.
Yeah, there are ways to do it, but with the specific. All these API functions that are provided, you're not able to manipulate them. You should suppose that it's already the optimal. Okay. Other questions? Okay, maybe just for completeness, let's see the both and the sum. So basically now, instead of timing, I say GPU, CPU, and I get it, I store it from here. And then let's have Cupy GPU equal GPU divided by ethers, and the same, let's say, with CPU and CPU divided by ethers. Just for completeness to see the two timings, and then we move to the first exercise. So basically now I added a new entry, and what you're going to see is a plot where we have both costs. And basically, okay, you can see that as we saw before, what we're timing is actually CPU time. And the GPU time actually already includes the CPU time. So you can see that it has these a similar, actually an higher overhead for then increasing. So basically for now on, we will focus only on the GPU timing. Okay, this was just a confirmation. Yeah, let me go back. Okay, so let's move to the first exercise. You can open your you can log into to Cyclone. Okay, you should be able to find in Onyx data edu16 a directory named day2 Python. Okay, which has this structure, right? So like you did yesterday, copy this directory to your home. So do copy -r directory, and then you say tilde, this command. Okay. Maybe increase a bit. Okay, after you copy, what you want to do is to install the modules, to load the modules that we need and install the Python packages we're going to use. So if we go to if we go in here, you should simply do source install.sh. So this is going to do two things. It's going to load Anaconda. In this case, we're going to use Anaconda. And it's going to load CUDA. In this case, the version 11.2. Okay, so this is done by modules.sh, which loads these two modules. In this case, the default version of them. And then sorry, and then the install.sh script is just going to call pip install and installing the three packages we need. Pandas and Numba we will use later, and Cupy that we are using now. Actually, yeah, Pandas we're using together now. In this case, in the case of Cupy, we have to install a specific version that matches the CUDA compiler version that we are going to use, the CUDA library in general. And you can read more about it on the you can read more about on their documentation. So if we go in installation, you can see that there are a list of precompiled version of Cupy here, this set. So depending on your on the version of CUDA you're going to use, these are the precompiled version. And you need to be careful to match them, otherwise it will not work. Okay, so as you can see, we are loading CUDA 11.12, and for this reason we are installing CUDA 11.2. Okay, so did everybody run the install command? And
can you show again the path for the files?
So the path is in Onyx data edu16, or you have it also in the home. Sorry, in your home you have data edu16 directory, right? Inside this you can find day2 Python, and this is what we need. Just like we said yesterday, this is a link. Even if it looks in your home, it's just a link. So up to you, after you are inside the Onyx directory that I said before, and therefore you need to copy it somewhere where you can then edit it before running the exercises. So you
I'm with my personal account and I don't have the permission. Could you copy them to the temporary?
Yeah, you're right. I copy to temp. Oh, sorry.
Thanks.
Okay. Anybody having problem installing running installation should have run through and without any issue. Okay. So to check that everything is working, then you can go to exercise 1. Okay, where you can find 2 files. So let me just batch job.sh before everybody else does it, which has 2 files, a job script for just running on the node. This is very simple, just giving some information. We're using the reservation that we have, 1 GPU. We load the modules and we run our Python script. So you can execute that from this directory. And then we have a script.py that is actually our script. Okay. Here I collected some of these functions that I've constructed in my notebook. Just yeah, it's not needed to go through all of it. As I showed you before, there is a function for timing, saving, this for saving the various plot. What we are going to run is the same kernel, both using Numpy and Cupy. And the idea of this exercise now is to get the performance for different operations that you now you are going to make your to make out of your mind, and we want to see how they perform one with respect to each other. So in this case, it's set up to run this the addition like I showed before. So I use just to save in different files. Now I'm saving add, and I have an addition here. I execute it. I'm going to get some PDFs that are the plots I was showing you, and some TXT files that are the data. Okay. If we want to try something different, this is what you're going to do now. So let's say you want to try the subtraction. You change the name just to save it in a different file. You change the function you are going to call. You save it. You use batch it again. And this will then produce a set of file names sub underscore and a representative of the other operation. What I would be interested to see, give you some time now for doing it, is to make these functions a bit more complicated, because of course now what we expect that subtraction is going to perform in exactly the same way as the addition, nothing interesting. But yeah, what I would like to see instead are some interesting cases, and I would like after you to report about the best and the worst gaining performance you can achieve against Numpy. Just have in mind one more thing that maybe I should have done. Just have in mind that if you want to use functions that are specific of Numpy, suppose numpy.sign of x, you should call them in this way. So you should put first the modules just to load them, and now you should then call the function from the API. But the question is then, okay, I cannot call np.sign against x if we're going on device, because what this is going to do is to copy the array back to CPU, and this is going to be Numpy to do it, right? So you don't want to do such a thing. What you want to do, I have it, I forgot to put it here. I think it's in exercise 3. You want to call this function that I will put it here and push it again, just so you have it. I'm going to call this function xp, the get array module, okay, where then you can now say xp.sign of x, which is a function that even if it's of Cupy, it's not going to return Cupy, but it's going to check whether X is a Numpy or a Cupy array, and then returns XP, which is the module that you should use, which is either NP or CP, okay? So this is going to do the work for you, and basically calling XP the sign of X, you make sure that if X is on the is a Numpy array, then you are going to use Numpy, and if X is a Cupy array, then you use Cupy. Okay. Any question? Yeah.
In these examples, we create the random numbers on GPU and use them on GPU, or on CPU and use them on CPU.
Yeah.
What if we want to use the same values in both CPU and GPU?
Okay, that's a good question. What if you want to use the same value for the purpose, for instance, of cross-checking that everything's correct? Basically, okay, you can, let's go back to the notebook. I'm not going to do it here. So, what you want to do now, let's take now the last run. Okay, let's go back at the beginning. Okay, suppose we created X1 and X2 on by Numpy. Okay, and what you're asking, basically, I want to put them on a device. How can I do that? Okay, you can just say cp.array of X1, okay, and you're basically going to get the same array, but yeah, sorry, right again, but on device. Okay, so now X1D, sorry, too fast. It's a Cupy array, okay? Okay, so this we put on device. Now you want to do the opposite, and you want to take it from device to host. Basically, one way to do it is would be np.array of X1D. Okay, but if I run this, this would be the equivalent. If I run this, it doesn't run. Type error. And it's explicitly telling implicit conversion to an Numpy array is not allowed. Please use get. Okay, why is this happening? So this is to break this interface. This is one of the cases where the interface is broken. So if you want to have more details about this, you go here in the user guide, and there is a difference between Cupy and Numpy. And there are some explicit cases where the reason why this is happening is because they don't want you to, by mistake, do something like we were saying before, is to call np. This should not work, but most probably it already run on device. So if I the type of these should be on Cupy. Yeah, because so you, in the case of sign you can call it, but in the case of other operation, let's say like roll, I suppose this still works. There might be some API function that will cast the array to that, and they basically want to don't run the situation where by mistake you're running the operation on CPU. So the automatic conversion it's not allowed. Okay, what you need to do is to use get. So to have X1 again, it's X1D dot get. Okay, like we saw before. Okay, please run some trials. You should, and would like to know some free yourself. Let's say in at 11 we continue. Mhm.
Can I ask, this Jupyter notebook, where it does runs on your local machine or?
It's no, it's running on Cyclone. So
Is there a, can you make a, can you run on your on a laptop, for example, and use Cupy?
you could, if you have a version, maybe probably the recent version of NVIDIA GPUs are. Okay, this here we go in another. Okay, it's another good question. Maybe before. Yeah, you need to have a GPU on the app, but there are some conditions. So, okay, are there other questions relative to the exercise before I go deeper into this? So, here we are talking about the GPUs that are made for scientific computing that are by NVIDIA first. So Cupy, let's take it from this way. Cupy first, it's an NVIDIA product, okay? Like we saw before, it's not actually, maybe if someone, it's supported by NVIDIA, it's meant to work with NVIDIA GPUs. And indeed, as you can see here, it's all the instructions are based on CUDA. So first of all, you need to have an NVIDIA GPU on your laptop, desktop, and you need to have a GPU that supports CUDA. Not all NVIDIA GPUs support CUDA. So gaming GPUs, cheapy GPUs do not support CUDA. You need to have a specific version of the chip. So these are the first condition. And then you need to have the CUDA environment installed, and then you can run Cupy. Now, if you don't have an NVIDIA GPU, but you have an AMD GPU, so this is another important topic that is becoming more relevant nowadays, where where AMD GPUs are also appearing. Well, there is a whole section here about using Cupy on AMD GPU. So there is some porting available. Though, as you can read here, it's experimental. Not everything is supported, and you need to you need to be careful. So it's not guaranteed. As well, you can install it for a specific version of ROCm, which is the AMD compiler. And so if you have an AMD GPU that supports ROCm, that is supported by ROCm, then you will be able as well to run Cupy in this case. But there are some limitations that you can read about here. Okay.
Oh, okay. So the main message is that if I want to, for example, build a desktop to make some runs, I have to check whether the GPU that I will buy will be able to make the.
So I think maybe this was more a topic back in the days. Nowadays, maybe most GPU supports CUDA.
Okay. Thanks.
But it's something you should check whether I think it's one of those in the technical details of the device of the GPU. It's one of those flags to tag whether it supports scientific computing.
Okay, thanks. Will this be recorded and uploaded, because I will have to go to another meeting?
Yeah.
Okay, thanks.
So, any issues with exercises? Someone? Okay. So maybe let's collect some numbers. I'm curious to see what you have run. So is there anybody from here or online that wants to report about that? Okay, maybe I muted it. Just unmute that. Online they can.
To run the job.sh file.
Yeah, with batch.
Okay.
So you should, because you cannot run it on the host, you need to do batch job.sh to execute it. Okay. And then basically you should get out some files and a log. So yeah, first try out the standard script and then start editing.
It just is submitted, then
Yeah, and then if you do a ls of the directory, you should so when you after say submitted, okay, and then you have when it starts running, you get a log file, and then here, okay, I'm not printing things, so in here it's going to be quite empty unless you have errors. And after a bit, you should get all these files. Okay. And then you can check the content of it by, for instance, less. And these are the numbers. So you can see that these are the timings. And for instance, if we want to get the speed up, we do here, and you see that is about 95 times fast.
So in this case, for example, in order to print and recover the data, there is no transfer from the device to the host.
What
Or is
data do we
is it
print?
done built in? For example, the results of the script.
The numbers, okay.
Yeah,
In this case, are
numbers.
just timing. So no, we are not asking. Everything is being done on device, so we don't have any copy. Yeah, it's. Okay. So anybody online that wants to report about some of the right? If not, I proceed. I mean, let's maybe test a case, for instance, before we're discussing about the role. So let's see how this performs in between the two cases. So for instance, I'm going to role X. We saw that it works, so let's put this and say np.role x of 1. Save it. All right. Taking some time. Yeah, maybe I should, if it takes too much time, okay, it's coming up. Then maybe reduce the number of iteration, the size or the number of iteration. So if you are doing something very expensive, reduce the two of them. And okay, let's have a look on the difference between the role. So if I check the roll, the speed up versus Numpy, okay, we see again pretty consistent results where it's about, in this case, 105 times faster. Okay. Okay. We will see the fact that we are reaching we're reaching the theoretical bandwidth, like in this case. Okay, this number tells you that it compares 1-to-1. Okay, because it's actually CUDA itself, it's a C kernel. Of course, if you are not running this x plus y, but you run something more complicated, you're not going to get that number. Okay. So that is what you will see if you start doing more complicated stuff. Okay. So, okay. There are any question or I proceed? Anybody wants to report? Okay, let's go. So now let's go to the second part, which is speeding up kernels. Okay. So Cupy offers you different ways to speed up the kernel, or better, to write user-defined kernels. And these are, for instance, the case of an element-wise kernel, which is what we did so far. Element-wise means it's involving always and only the same elements of the two arrays. Okay, so rolling, for instance, like Nicholas was saying before, is an operation that involves arrays at two different positions. But if you want to do something like a difference between the two arrays squared, you can do it by defining one of these element-wise kernels. What is the structure? The structure is, okay, we say we are going to define an element-wise kernel. Then we say what are the input parameters. In this case, if you're a bit familiar with C++, what basically we are saying is to be agnostic on the type, and we just say T. These are two templates, two input arrays that have of any type T. If you want, you could specify that it is an int and then compiles for integer only, or it's casted to integer. But T is going to be the type of the array, independent of what is it. X, Y are the input, Z is the output, and our element-wise kernel is going to be this kind of C-style function where we have, we defined, for instance, here the difference. So we are defining a new variable. We say tdiff equal x minus y colon. And then we store into Z the results of the difference squared. Okay. Note that this is C style, so it doesn't exist something like this squared. This is not supported. It's not Python anymore. This is C. If you want, you could use the function power diff comma 2, that is the equivalent. Okay, but it's not Python, so this need to be seen. It's a semicolon at the end, definition of variables, and storage of results. Sorry? No, you don't need to say CP because it's not a module. It doesn't know. Basically, it has loaded the math library, and so everything that is defined inside math.age can be used. You can load other libraries, you can do a few things, but it's so math operations. So those that are in CMath. Okay. Okay. So we define the kernel, we give it a name. It requires to know also the name, but this is just if it has the same name, then one overrides the other. So it's good to give different names. And the same, basically what we get is then a function, square diff, that we can call giving 2 arguments, and this is going to return this output. Okay? So in here you can do anything you want. So this is pretty simple. It's a bit C style, but it's still quite simple. Let's say user-friendly. Let's go to a bit less user-friendly stuff, like if you want to implement a reduction kernel. So a reduction operation is an operation that sums over, or that does an operation over all the elements and store them in a single value. So like the sum, when we say z.sum, this is a reduction operation, okay? And we get 1 value. This is what people name reduction. A reduction kernel is a bit more complicated because now you want to do, you have more variables. Again, you need to provide input parameters, output parameters. You can provide an element-wise operation to be done on the input before storing something. So this is stored in a temporary variable that we don't have access to. So it's like before when we did z equal. This is stored in something, in an element. So this is an element-wise operation that is done before reducing. Then you say, what is the reduction operation to do? This needs to be a function of A and B. Okay. A and B, it's arbitrary. It's not something we are giving. It's an arbitrary naming that Cupy provides you. So you suppose you want to do a product between the two, you say A times B. You want to do something more fancy like A plus the sign of B. So you sum signs, you can do that. No, you can do whatever you want in here. This is the reduction. Then there is the option of doing a post-reduction operation. So suppose you want to do a norm squared, which is actually this case, del to norm. You are going to square, you are going to sum, you are going to, after finishing summing, taking the square root of the result. So this needs to be a function of A, that then is stored on the output Y. Okay. Last one here is the starting value. So we do a sum, we start from 0, but we want to do a product of elements, and it's good to start from 1. Otherwise, our result is 0, because we are going to multiply 0 by anything, and it's going to give us 0. So we want to start from 1. So that's why you have this bit, the kernel name, and this is how you implement a generic reduction. Okay. In Numpy. What is very cool about this is that it supports the axis, it supports, let the user define where you want to, which axis you want to sum, average. So it supports a kind of interface similar to the one of Numpy. So, because, you know, if you have an n-dimensional array, let me do it a second. I suppose if you're familiar with Numpy, this is something you know, that if you have an n-dimensional array, let's say something that has dimension 555, then I can say x.sum axis equal to, let's give different dimension just to 345. And basically I'm summing along the last axis, and basically what you obtain is the result, the shape of it is 3,4, because we summed only along the last axis. We sum along axis 1, and it's 3,5 because we're summing along this axis. This is a generic tensor. You can sum along axis 1, 2, and you get only 3 because I'm summing along the last 2. In general, you can do such a thing, and this is very nicely supported by this reduction kernel. So you can provide here the list. You can have a multi-dimensional array, provide a list of axes where you want to do the reduction on, and you get an output that has the remaining dimensions. Okay. Any question about the reduction kernel or element-wise kernel? Okay. If you have a question about Python itself, you can also ask. It's not a problem. Last way to have a user-defined kernel is to provide a raw kernel, a C-style raw kernel. Just really, you take what you did yesterday with Yannis, you copy and paste into it. You just may want to say it is extensive in case you use C and not C++. Just if this is not mandatory, but okay, it's good to say it. If you use a C style, otherwise, if you use C++, you avoid it. You copy and paste your kernel. You really treat it as a standard C style kernel. So you provide the list of arguments that are coming now as pointers. You compute the TID accessing the block ID, trade ID, that this is going still be decided by Cupy. No, you can decide it by your own, sorry. This is going to be given by yourself here. And this is really a kernel like you saw yesterday. So you copy and paste the kernel, you do the operation you have to do, you give it a name, and then you can call this from Python by providing the arguments, in this case, x1, x2, y is the output. So now you don't have any output because you're not telling which one is the output. All kernels, I think Yannis told you yesterday, all kernels must be void. They never return something, the kernel. They cannot return something. So the kernels always need the output to be given as an argument, and you always store into it. So everything needs to be allocated, etc. But what is cool about this doing now in Python is that the allocation is done by Python. So I need to allocate x1, x2, and y. But then you can provide these two, and you provide the kernel parameters that are the block ID, the number of blocks, and the number of threads. So these are x, y, z, like you saw yesterday. Okay, and we're getting y the result. So it's quite nice interface, but it's C. So you need to know C. It's not Python anymore. While before, even if you didn't know C, you can still know how to do it. Here you really need to know C and how CUDA works in C. Okay, but still it's quite cool. Okay, question? Yeah. It's run by it's CUDA. It's you are going to have the one-to-one performance of a compiled kernel run through Python, but as a CUDA kernel. Okay, so this is going to have, if you put in here what you did yesterday, you should measure exactly the same performance.
Can we also import precompiled code, for example, as library?
You are asking if we can include here library. I need to check. I suppose you can do it because I saw some example like that. But first, you need to load also the library. So, okay, for more details about this, here in the user guide, there is the user-defined kernels topic. And the raw kernels have a section about it. I think you can also include other files in there. I saw it to be done, not here, but okay. But I'm not so sure how to load the library explicitly. So you see, you can give options. Actually, okay, you see, you can give up compiling options. And so you can say to link to that library. You can say -L and link to that library. So yes, you can do that. So it is just really compile. What it does, it compiles for you. So everything you are doing here, this is a just-in-time compiler, I named like that. Everything you write here, it's compiled and then executed. Okay. So it is the same performance, just you have the advantage that you can visualize your numbers, and all the memory management is done by Numba, Cupy. Of course, Cupy cannot do miracles. Let me see if I crash. I don't want to crash my node, but suppose I allocate wrongly the kernel. Okay, I got an output, but I should have also got an error. I should have got an illegal memory access. So if this guy is not allocated correctly and I'm trying to write in it, then you get illegal memory access. And then you may, if you do something wrong, your device can crash, and then you need to restart everything because it's crashed. So okay, cannot do miracles, of course. Okie dokie. Any question? We're very close to the break, so we go through. Any question about this? Okay, then let's go to try out what we did now. So namely, I'm going to do the same, running the same function both as we were doing before, and by using a user-defined kernel, like in this case, square diff. So if I run this, I collect the numbers. I'm going to name in line the case where I write it in at runtime. I write it like in Python style. And then I compare it to the square diff kernel. So is it running or maybe I crashed before? Oh, no, I was worried I crashed the GPU before. Okay, we get the same output as before. Okay, now let's see the gain by compiling the kernel. So what is the gain and where do we go? So we call this kernel that we compile. So the square diff is done in C now, compared to the case where it's done by Cupy. And there is a speed up. So we can see that the Cupy kernel timings are lower than the case I do it in line. So for this very simple operation, actually, I already need, to get the most of the performance, I need to run a compiled kernel. I'm going to tell you why soon, but let's go, let's see the numbers. So basically, we see that here the two numbers are Numpy, Cupy, and Cupy kernel. We can see that if we go to the speed up, by compiling the kernel, we go from something that is about 80 times faster to something that is 230 times faster than Numpy. And so there is also a relative speed up of factor of 4 almost between the two. And if I go to look the bandwidth, that is should be our criterion to decide whether we are doing things correctly or not. The bandwidth is saturating. It's around 800 gigabytes per second. That is what you would expect by a well-written kernel. While the other one is 269. Okay, why is it already so much faster, and why do we need to do this? So this goes in the direction of what I was anticipating at the beginning, that it's not as simple as saying use cp.random and use cp instead of numpy and then do operations. It's not as simple as that. Why? Can anybody, does anybody have an idea? What is the difference between the two cases? I mean, in one case, I'm calling a compiled kernel, the other I'm doing the operation here. But why is much slower to be done by Python itself? So the main reason, okay, apart that one being compiled, but it's not that, because it's not this like we were saying at the beginning, the difference between doing explicit for loop in Python and NumPy. It's not that. Here we're still using NumPy. We're still using compiled operation. The problem is that Python and in general Cupy, or whatever other package, it's not a compiled package, and so the instruction in Python, they do not get compiled. And so Python cannot know what is your whole set of instruction, what you're going to do. So the fact that you store y equal this, Python doesn't know that it can optimize it. It doesn't know, it's not telling Cupy, look, you should run this as a kernel. Python basically just telling Cupy, okay, compute me this, compute me the difference. Wait, compute me another difference. And then once you finish computing the two difference, compute me a product. So it's doing every operation step by step. And you will get exactly the same timing for Cupy if you would have written this as y equal this, z equal this one, and k equal y times z, let's say. So this is exactly what Python is doing. It's doing three operations and this. Of course, then you can optimize it further. You can just say, okay, I'm computing twice the same thing. I should do just y times y or y squared. Okay, still fine. But still you are calling two separate kernels. In this case, you are calling three kernels, which each of them involve memory allocation. So this guy is going to allocate memory, store the result somewhere, again, store the result somewhere, and then multiply the two new array and waiting for the kernel to be finished. Why this is not a bottleneck for Numpy itself? Because when you do it on CPU, everything is fast enough. So it's actually that the CPU is low enough that this redundancy is not a problem. When you do it on device, it is. So when you go further than doing one operation, then the best performance you achieve it by compiling everything. So unless it's one function, one operation that you're going to call against your arrays, unless it's just that once you go further, these things gets worse and you get better and better result. I mean, as more operation you do, better and better result you do by compiling the kernel instead of calling them one by one. Okay. So we arrived to the break. We'll introduce you to the next exercise that you can do if you have some time during the break, which is basically, let me open it, it's exercise number 2. And it asks you to do exactly the same you did before, but this time by compiling, by writing also the explicit element-wise kernel, okay, like we did now, and check what is the gaining performance between what you tried before and what you're trying now. So if I run this for x plus y, what we expect, and I'm going to do it, so we get these results, is that, like I explained you now, we do not get any gain. So it's not that you have to compile everything. Okay, so if I run x plus y, we are not going to achieve any gain because x plus y, it's already optimally done by one call. It's one call, so it's already optimally done by Cupy. If you do something more like we did now for the square diff, then you have advantages. So if I check now the add performance and I check the speed up, for instance, you can see that they exactly overlap the two, compile kernel and not. And I check the bandwidth, and this it's the same plot we were seeing before. We are saturating the bandwidth in both cases. There is no difference apart from error measurements between the two. So if I check the timings, I go to look at the numbers, we can see that they perform exactly the same. It's 5163 and 5165 milliseconds, 0. millisecond. So there is no difference between the two, done in one way or the other, up to errors. If you do something more complicated, there is. So as a continuation of the previous exercise, you should implement again in exercise 2 you should implement again in exercise 2 what the function you were testing before, and then compile it as well and check what results are you going to get. And I would be very interested again to hear from somebody what they're getting.
Sorry, in order to open a PDF file in Cyclone?
Yeah, that's a good question.
Yes,
What you should do is copy, either you start a server, you port forwarding, it's not that simple, you need to copy it down. So it depends on where you are. If you are on you're on Mac, then you should be able to do an FSSH and do a mirrored file system locally. So you can look how to do FSSH to set up a file system like that. Or the simplest thing is to SCP download and locally visualize it. In my case, I can visualize it because I'm running this server exactly on the same node, and it's going to give me the info. Yeah, I'm in Jupyter and it opens. If you want, you can do also like me, but I didn't want everybody to allocate a node and run Jupyter. Okay, we can go for a break.
Break for 30 minutes, and we start at 11:30. No, what time is it?
No, at 12.
We start at 12 exactly, please. Thank
If
you.
you have any question, I will be here, but okay. Yeah.